So good morning, good afternoon, and welcome to this webinar. Today we are thanks also to the colleagues of Waterford that we are presented also some colleagues of Waterford that we work with us, we collaborate with us in this project. So today we are talking about the role of geologists in well economic zone production evaluation. So this is a real case of application starting from the seismic pre-drilling assessment to the zone production evaluation. And we are show you a real flow case assessment, and we show you also how to evaluate the pre-drilling and the drilling data to study and to underline the economic zone to development, for example, a turbidite gas sequence. And this case is extracted from a real case. This is during exploration well in Caspian Sea. And finally we have, so this is the 5 principal topics. And finally we have also the presentation of the new tools that we are developing and patented for Waterford, that is the IsoParker and mini Frac plug. We are through these two new tools, we are trying to give value to every thin layer, every thin geological layers, and this is we are very orgulous to be to support the Waterford project and patented these two tools for Waterford. So the key topics, we have 5 key topics. The first key topics is the pre-drilling risk assessment. 3 different ways from geophysical data to on-site data, and we are starting from a review of this project, starting from the very early stage phase of project when we acquire seismic data and we make this, and we show you how to do seismic assessment and risk assessment of pre-drilling. The new LV data interpretation, how we can support real-time exploration net paid zone in complex turbidite sequences like Caspian Sea, and also a new model of a new logical model that is called the petrophysical decision tree that allow and support a real-time drilling in this way. So we have also to define, and finally we have to define the geozone to achieve the highest performance. So the geozone will define as the zone for the financial investment or the number of operation, the safety and the quality. And for in first targets, in first topics, we make these display words: precision, need, decision. So it's clear that we are trying to developing the decision tree because the new decision tree I support the geoeconomical zone from petrophysics and geomechanical data. And linked to all these routes, we have just developed for Waterford a new patented tools, that is the IsoParker and mini Frac plug, that I will show you the application in this real case and in other possible case linked to the value of actual price gas and also to the geological context. So starting from the first key topics, so this is the pre-drilling risk assessment. So when we are talking about the pre-drilling risk assessment, we are talking about the consequence of acquire different type of data and evaluate the effect of drilling in the area. For example, we have make seismic surveys, gravimetric and magnetic survey using satellite or for derived bathymetric image like this. On-site data like seabed survey with the ROV. Evaluate on-site, for example, the shallow pore pressure test, site sampling. All of this are matching all of this to create a geomechanical, geophysical model that can be underlined, which is the measure hazard in this area, like trap and seals, which would be the critical parameters for trap and seals integrity, the shallow gas hazard, the fault, the presence or not of the fault, and other geohazard, for example, like bubbles of methane or like this. So what kind of data we can use it for the pre-drilling assessment? We have a three way of type of data, starting from geophysical data to on-site data. The first type is seismic and geophysical risk assessment. Before drilling, in the first phase, in the earliest first phase, generally before the drilling, we use this kind of data, seismic data and geophysical data, to evaluate what? To evaluate, for example, the presence of fault fracture analysis. Using seismic data, you can map the fault, fracture, and possible weak zone, and also to detect anomalies and direct carbon indicators. And also, but it's much more important in this case to choose when need to deviate, for example, well identify the overpressure zone, potential gas pockets, or fluid migration path. Rock mechanical properties are sometimes also derives from this kind of data, and we calculate also porosity, estimate lithology and rock strength using seismic inversion and ARO analysis. What kind of risk we can evaluate? We can sure predict the overpressure zone, the blow up or drilling difficulties, identify potential shallow gas hazard, assess drilling trajectory, and advantages are sure that with this kind of techniques we can cover a large scale or regional risk, understanding that is not invasive method. So the only limitation is the resolution, small scale heterogeneities, and especially small heterogeneities can be confused or can be missed and require calibration with nearly well data. So this is a summary, a graphic summary of what we can do with seismic inversion, and to check, for example, one of the major risks, that is the overpressure risk assessment. We can use different models of inversion using, for example, elastic and unelastic parameters. When you see elastic parameters, you assume that all of investigated soil by the seismic waves are the same compression ratio. Unelastic generally is much more defined anisotropic zone. So using, for example, the first version an elastic parameters only, you can derive a simplified model of porosity, of effective porosity and density. So the inversion of one seismic acquisition can give you, for example, the first result that is this kind of results. For a single depth, you can define the version of risk map, and you can have the three colors, and for medium risk, low risk, and this is a summary of geomechanical, geotechnical, and pore pressure parameters. So it's clear that if you are find the target, for example, in this part, and you have a high risk in this part, In this case, this plot is referred to this part underlined. Or for example, you have also a zone for an uncertain risk or bypassed risk, like north and south part. It's clear to prefer using the medium path of drilling like this. So we are studying, we are applying also for Waterford this new approach that conducted finally to the definition of IAS geozone, and after we explain what we can see. The integrated risk cost matrix, we also built up an integrated cost risk matrix to reduce all of kind uncertain and reduce the economical impact of operation. So the second model is using the inversion with inelastic parameters. We can apply to seismic data different filters and different type of inversion, and we can consider that you have different substantially we consider that in the XYZ we have different compression of, so we can consider not elastic, not totally elastic, the subsoil. It's much more realistic model. So we integrated this also with sonic logs and PVD monitoring. We control safety this, and we have the version 2 that is a real risk map. Also with we can differentiate the pore pressure, the lithostatic pressure, the water pressure. So for example, in this case you have in the blue zone the overpressure water influx. So this is a zone, in this case you are cutting, you are like make a photograph of this part. You see from geomechanical and hydrogeological point you have an inflow of water in this part. So it's really important to know this. And with this first model that use elastic parameters, you don't see that, because you assume that all part is have a constant the ratio between the compression in XY and ZY is the same. So the geomechanical model is more refined. You have, for example, a high overpressure of gas, you can see that, and mechanical breach or shear failure that is in this zone, and we have a safe MVD window validated in other zone. So it's clear that in this case the real target is in this zone, but we have the trouble to make attention because you can have the problem of water inflow. So when you are layering your seismic acquisition and processing the layering, the seismic acquisition, you need to more be attention of what kind of operation you are planning to do when you were drilling. It's clear that this kind of approach reduce all of cost of operation, and we summarize a positive impact. In this case, we are summarizing a financial positive impact. I show you the Waterford data. We create a value creation of $2 million plus in value creation with this kind of approach in this way. So it's really important to do this kind of analysis before drilling. If you are doing correct this inversion before drilling, you are make a fantastic job. Is the same. Okay. It's clear we have a pass flow assessment that you need data collection for the trough seal integrity. You need to, before to do that, you have a geodynamic and geological structure interpretation to recognize the trough and the seal integrity. the data processing, shallow gas hazard, the data interpretation, the faults, and the geohazard. So the risk assessment will make the safe risk assessment is really important because allow to do a safe drilling plans, mitigation of all type of risk, ambiental risk, also not only for the company but also ambiental risk like this. The seed allow to support and the seed the precise well location and also the trajectory to plan. So in summary, you have the first three type of methods: the geophysical method, principally seismic, granulometric, and magnetics. The purpose is to map faulty anomalies. Structure and fluid hazard is much more important. As you can see in the previous slide, mapping the overpressure zone. For example, when you have a seal trap with a cap that is made by water, a mixed zone is much more impressive to analyze this. This method covers a large area with pre-drilling risk. Modeling, offset, for modeling you can use offset wells or logs or cores. The purpose is build lithology and geomechanical data processes. The risk focus is about the same. Overpressure and wellbore stability is another much more important point. So the first point is to find where drilling insecurity and avoid all of the type of risk. The second point is when you are drilling to be sure the wellbore stability and the quantitative, and here you can use quantitative and predictive method. On-site monitoring, you can use tools MVD, LVD, gas chromatography like this for real-time detection. And here we are trying to developing the GeoE hazard decision tree. Second data point is the also during drilling. So we see the first stage is before drilling, seismic, granulometric. Second is during drilling. 1D, we can need to build a 1D, 3D well models, include lithology, porosity, permeability, and pressure with a circular around around the well. So the geomechanical model predicts a safe made weight window and also the formation stability that is much more important, because if you are drilling, for example, and not parallel geological formation, you can have also the trouble of the stability of formation, the fracture gradient. The overpressure prediction using seismic velocity trend or sonic logs. What kind of risk we are evaluating during drilling, mud weight and well bore zone planning, the predicted likelihood of stack pipe, loss circulation or kick events, and the measure advantage of this is quantitative because we are directly linked to the drilling parameters. We can be integrated into directional well planning. So the limitation that it depends on the quality of offset between the previous well data you use and the anomalies checked or missed by that. It's clear that just during drilling you are start to find the first geozone. The geozone is the zone that we can be potential have a production and or we are proposing wellbore positioning. So, for example, you can have three different types of geozone. The first geozone is a laminate pay derived from this image. The second geozone is a calcareous cemented sand, and we can evaluate the value of this geozone. First point of point one is on-site during drilling, real-time formation pressure management, detect kicks or abnormal pressure change during drilling, lithology and fluids like gamma ray resistivity and neutron density in real time. So the risk evaluation is just in real time mediated decision. So in this case, we can use the new GeoEye tools 3 for blowout prevention, mud weight adjustment, optimize drilling parameters for unstable zone. We verify the prediction on and update models. So the advantage is the direct and accurate real-time detection, allow corrective action during drilling. The limitation is expensive, that are much more expensive in monitoring, so limited to drilled interval. This is a summary of what we are doing during the LWD and sonic gamma ray for geomechanical assessment. So this is like a checklist or scheme that we can follow in this real case. You are operated, so in the Caspian Sea, you have a progradation of the digitized progradation of all the ancient river. You are in this geoeconomic zone, and the real-time boreal stability you are doing while in the first stage with the seismic data. You evaluated the whole of area and a single stacked layer by depth, the overpressure zone like this. In this case, we are make a punctual evaluation through the LWD drilling exploration. And so you are like, we have the first scheme that we are generally use, supported the GeoEye engine. So this is a commercial pay-use zone, yes. Why? Because if we have multiple anisotropy or modeling, we resolve the reservoir, and if you have a positive GIP calculation. GIP is the index of, represented the index of how many volume of gas you can extract in a single zone. It's clear that you have a green colors. You have a yellow colors when the geomechanical stabilities and condition is not security, so you need much more. You need to start implementing some operation in the wells to arrow stability. You need, for example, cementing, and after fracking, the matrix derivative show different troubles. We need to optimize strategy, for example, one casing or two casing and after cementing. So the index of GIP, economical geozone, decrease, and so is evaluated like JETS 2. And you can have, for example, also the orange when the NPT is equal to 0. So in this moment probably is not convenient to develop this zone. And for abandoned wells or old wells, we have tested this approach, and also the Frac plug in abandoned wells. You can have, for example, a red colors when you have a non-sub-commercial, and the bad oil sands, especially for bad oil sands or tar sands, or in calcareous suspended, we have a high uncertainty, so we have choose to discolor in matrix of evaluation. Because you can have, for example, risk of internal fault, not stability, or like this. A comprehensive pre-drilling assessment should integrate all of three approaches, start with geophysical and regional understanding, refine with model, and as we just say, that this the final consequence is to define along the wells the geoeconomical zone and the net paid zone, which will be the zone through the physical data will be deployed and to extract it, for example, gas or other resources. Okay, so with second topics is new LVD data, how we can support real-time exploration and net page zone in a complex turbidite sequence. So we are going through the case of Caspian Sea. So we have the real-time acquisition, the logging while drilling LVD, and you have an advanced log interpretation, as with scatter plots and statistical real-time data. We have the real-time data streaming. Also, we have, for example, the profile of VSH and VSHY of the seismic wave. The net pay identification. So the final results is the net pay identification, because in this kind of sequence you have a very thin layers, but the interval of thin layers with high TOC is really frequently. So is you have a complex stratigraphy, establish the cutoff, so the porosity you can have a different condition. For in general, in this case, the good condition is when the porosity is measured than the 10%, and the content of water, so the saturation of water, the SW parameters, is minus than 50%. So this is a good indication of hydrocarbon and real-time net pay mapping. So you have a graded bedding, a thin lamination, and finally we can transform in sand shale heterogeneity model. It's clear that what you can see in this direction, that can be an XY section, imagine that you can have also in zeta in other direction, and the change of this and this thickness can be changed also in zeta. So consider that the thickness of this can be around 20 centimeters. Think of this, that is 20 centimeters for 2 kilometers, and that will be changed. So you can find the trouble is that you can, the drilling assessment in this case indicate there is a good connectional stability, but you don't see real, which is the mixed, you don't see effectively the mixed zone between gas and water in so thin layer. So you need to acquire much more data, you need much more attention, and you need to planning to establish which will be effective, because you have, for example, this for at depth of the 2 meters depth, and you have another same situation after 300 meters depth. So it's clear that it's crazy, but you need to mapping that if you want to maximize your potential reservoir. So this is a brief of map of the area we are operated. We have so in the progradation of ancient delta, as we say in the previous image, is the like a progradation of a storage zone. Okay. So we have extracted also a IsoParker map, the bottoming control and the wells and the mud. We have also the presence in this case of mud volcano, a small volcano that similar to have a, for example, in Pineto, that erupted sands. This is the sky plot of principal sequence. We have the Novo Caspian, the Aberdeen, the sands, we have the clay sands, and so we have plotted the gamma ray and the SW value. So it's clear that we have different intervals that are to be good for the production. For one is this in sands, another is this in the sands, another is this, but the thickness in XY is not constant. so the effect of well trajectory on collapse pressure, and you can see like this, the how can support the real time and make a decision to develop the net pay in complex turbidity sequences. So the first is resolving the thin beds and lower rest play, because we have different thin layers that we clean for clean sand, laminated shales, structural shales, and also calcareous oil sands in the depth, especially in this part. So we have all our sequences that are covered this part of carbonated, and but we have dynamic and true positive estimation also in this part. Azimuthal propagation resistivity, the resistivity, the image resistivity show you a good value. So, but there is also a high content of water. So this is the principal trouble. This confirming the mobile hydrocarbons by nuclear magnetic logs, the NMR logs. So the bound of water is, we have a peak for the bound of water, and we have another peak for free fluids. So the effective porosity is important in this case, but there is a trouble because we have free fluids, so fluids that go in all direction, and you need to trap and to block it that. We have also to detection of fluid tapping, in this case along well, and it's important to, in this case, I will show you to use the IsoParker and isolated the single layer, trapped the single layer to improve this kind of a system of capture. The real-time well placement and geosteering, this is another method. So the geosteering allowed us to mapping the reservoir, but in XY direction. It's like a radiography in XY direction at single depth. So through the geosteering and the ultra deep resistivity mapping, you can have an image map of reservoir. When we are doing this kind of image map, you have something surprise, because you are thinking you are homogeneous, but you have a sand boundary, you have a sandstone, internal sand boundary, so you know that in real case, in this case, we have like an anticlinal structure with sandstone at the center. And so it's a really complex situation. So evaluate the geozone target is not so easy. But the project goes on, and in fact we have summarized a good impact of 2.1 million of USD dollar. We have finalized the wellbore completion schematics in this case. So this is how will be completed the wellbore completion after clear the geosteering and ultra deep reservoir image. We are managing. It's clear that the principal trouble is managing the pore pressure and the fluid free fluid pressure. So we need to drastically isolate this part, some part of reservoir, and make casing and isolating that. This is a first stage to be a security of finalize the wellbore completion. So the wellbore completion allow in this direction, and finally this is the final point. With this method we summarize a net pay calculation, the total net pay calculation. So the total net pay calculation that is derived clearly from the GIP, the value of GIP that represented the value of the quantity of the real quantity expressed in cube meters of gas that you can be extracted. So the final net pay calculation result that, and the net pay calculation represented the net pay without cost of operation and like this. And also other costs like cementing, casing, and so the integrated Caspian reservoir evaluation. We have an integrated evaluation finally before to arrive to summarize the impact and to calculate the net pay calculation is the previous step than that. Integrated Caspian reservoir calculation. In this case, the TOC at GIP max. The TOC is the total over carbon content. So, and GIP represented the quantity in feet metric cubes that you can extract. So, the Caspian turbidite sequence, the turbidite channel is, as you can just see, is simple to be. It's simple to be simple. Sorry for the play of words, but it underlines a really complex. It shadow a really complex. So the Caspian turbidite channel zone, we have this environment for this zone. We are make the total organic mapping of carbon. In this case, we have a high torque source interval at depth of 200 meters and high torque source interval in Oligocene and Miocene. So we have the low torque reservoir in sands. So the trouble as turn to the stratigraphy. Okay. So the production zone is that, but you have this all of part that is saturated, and you have free waters and free fluids. You have free fluids also here, and you have the formation, the middle circle and the upper bucket that is isolated formation. But this and this we circulated water and other fluids. So the information that we analyze is Sankara and Dritter. In this we can have a high TOC of source intervals by Oligocene and Miocene, and we have a low value TOC for sands reservoir, because that it means that the evolution of this reservoir is ended. All of gas is migrated in these rocks, and what leaves? It leaves principle that you have a free fluid that circulated up and down of this rock. So you need to be isolated that you have the GIP, and the gas in place. GIP is the gas in place, the effective value of gas in place. Map the GIP, the quantity of gas in place. You have a clear image of commercial and how can be potential develop this part or the upper part. So here we have a not very good correspondence between the map of TOC and GIP, because the gas, there is much more anisotropy in this layer, so the gas try to migrate and expand in the central part of layer in all direction. If you see this map, you have to see this phenomenon. So it's really important to underline that, to planning where to drilling, if you are drilling here, finally it's clear to review all previous data by the geomechanical and the other stability. So the analysis workflow is not so simple. You have input data streams, seismic passing that this zone that is extended around for 200 kilometers. We have a high content TOC and JIP, but the JIP is concentrated in the central part. We apply the grain models for the ratio between the content of water and thickness of layer. We improve with the LWD data and magnetic log effective porosity. Finally, we have the Thomas Stieber petrophysical model that is implemented in the ING multimineral or anisotropic model. You have the talk results. We have calculated the talk results and mapping the talk results, and we have also make a prevision of how this talk can be moved. And finally, we have the JIP results, so the gas in place, that is essentially a formula, the area for the thickness, for the effective porosity, for the content of water, for the MTG, for F. It's clear the total recoverable gas JIP is not the total, the challenge is this, that is to hide this value, because you have the total value of TOC is measured than gas recoverable. So the unrecoverable gas we have because we have water in the base layer and upper layer. In this case, we have, as we just say, just a concordance between these two values. Instead of this, the JIP is minus than TOC. Integrated and schematic correct porosity and economical zone. For complex channel and environment, in this case you have an integrated schematic and periodic corrective porosity and economical zone. If you are mapping this, the gas in place, you have also the mapping of the porosity, so the gas in place. You have a different map. You have the J6, so this is the high-valued zone. All of the zone in this color has a high value, but the zone is extended for around 20 kilometers, for around 2 kilometers, so the economical genuine jetting zone can be changed also in this direction. Summarized impact, the ING, and also this, we have the petrophysical data, we image this, and the petrophysical data show you, for example, a high content of water in the first part that is intersected with gas part. Go to details. The details was given by during the exploration well. So the first exploration well, we are doing this first exploration well in this digitized zone. This is a digitized zone of progradation. During the first exploration well in digitized zone progradation, what's happened? Happened is that we have created a porosity cylinder around 20 meters, 2 meters of the drilling zone of LVD zone. So the porosity, we have also a details porosity. Why we are doing this? We are doing this because in the final stage, it's much more important to go on details, and details need to make also decision, for example, and we say just in the last part, if you need to frac, to apply a frac or a frac, it's clear that not only direction need to be fracked. If you observe these two directions, for example, the south east and the northeast, this part will not be to be fracked, absolutely, because you have a very low porosity, a very low torque source. In this case, we have also saturated water shales. So it's clear you need not to be fracked, you need to make attention and make a particular casing and cementing in this zone, and after that you can frac here, for example, because this is the pressure of calcareous sands with high content of gas and oil. This is the high pressure there, free gas cluster with high GIP value. So it's clear that the screening to define the geoeconomical zone goes by steps, and finally when we are doing the first well of exploration, as in this case in the digitized part, you can see the real effects around the wells. So around the wells you have a complex situation along the sequences. Okay, so we do this kind of analysis, this plot, cylinder plot, also to define the future operation that we are needing to do. So we are just go to the last. Okay, we are just go to the last part of presentation. The frac can be applied and need to be applied in only this, in only two directions, and not be applied in all directions, because if you apply the frac, in this case, where are you? If you apply a frac in all directions, you can probably have inflow water, for example, in this direction. Inflow water this, and you lost all of works. So we have as a summary of analysis workflow: the input stream, the LFD and MRA effective porosity, the spectral. You can use also the spectral gamma ray and PEFT, and use the relation of Thomas Stieber petrography, Thomas Stieber prediction. Integrated all of this. Finally, when you have a cylindrical map around, you integrated in the GIP and TOC map. So in the previous map, if you are, for example, put here the expression is here, you integrated this, and finally you have the map around 10 meters of exploration well, or what we type details map of what types of operation you need to do to make safe and predictable the wells. Geoeconomical zone is this. You can have also the integrated IS performance that represented this. The operation is equal to 0, is not safety, is not comfortable for company, it's clear. If you have a green semaphore, you can go south. You can have a clear high quality of data and geoeconomical zone map. I hope you understand all of these steps, but it's clear that in all of a complex turbidite sequencing using LFD logging with drilling that acquires a multiple physical approach, you can go without all of this trouble. The LFD, in particular nuclear magnetic tools, allow to direct mobile fluid measurements, identify the bypass paid zone if you need to do a bypass. The azimuthal imaging visualize thin bed architecture, quantity with net to gross ratio. The triaxis is much more for stability, the triaxis resistivity for correct anisotropy, and calculating the water saturation in lamination. And also the ultra caliper logs is the principal Boreal logs using for stability, ensuring also the data reliability in complex section, as we just say in this case. So finally, I make these slides for all people that are not expertise or not know which is the relation of Thomas Stieber. So the Thomas Stieber relation allow to make a prevision of real-time prevision of how porosity will be changed, effective porosity and bulk porosity, instead of the different types of effective porosity and bulk porosity, and how can be changed the value to estimate the shell distribution with high value of TOC. So the real-time density neutron shell distribution analysis estimated the true sand porosity in a complex sequence turbidite like I just presented to you the Caspian Sea. The clean sand, we have the laminated shale, the structural shale, and we have also the dispersed shale. For the poor shale, we have also some point campionated like poor shale points. The sand shine, this is a clean sand cluster. We have a shale layer, shale points, and thin lamination, that is the dramatic layer that we are trying to capture in this case. The dynamic estimation of true sands, we have a correct value from LFD estimated the true sand porosity. We have the shale. It's clear that you are reading the bulk density and calculated the real porosity through the intercept of these two curves. So the neutron porosity give you a measured value of porosity by Newton magnetic logs, but you need to correct instead of quantity of shale sediment present in a single volume, in a single cylinder of that. So it's much more important when you are analyzing a complex turbidity sequence like this. So it's clear that clean sand have for you, if you are recording the clean sands in Newton porosity log, you don't view that because you have zero value in Newton porosity log, but the density is twice, it's clear around 2.5, 2.6, it depends on depth. And but if you are going in the real case, you are see that, for example, shale layer or thin bed lamination. In this case, the thin bed lamination, we can make the dispersed shale and the thin and the laminated shale. The laminated shale are started here, so we have a sequence that are following this line of regression. So this is the final summary of steps to define the final volumetric page zone. How we can define the GIP, the volumetric page zone, that is essential parameters for all of the company. Starting from Thomas Stieber petrophysical correlation and inversion, and so you analyze the porosity in all of the direction, in cylindric direction around the drill wells. You are estimating the dynamic true sand porosity estimation. You have also the laminated shales. You have make a comparison between this and these laminated shales. You have make correction of anisotropy because the can be changed also in this direction with Klein models with real resistivity and low resistivity. We resolved, finally we have a resolution of thin bed low resp. What does it mean, thin bed resp? Which of these, all of these have a high TOC content, but which one of these can be paid effectively and be used for the recoverable gas volume. The TOC and the fluid evaluation, we are using general this formula, calculation of TOC in a single film bed, purified from the surface content water, and the cost of operation to be parkered and isolated. So finally you have the G, that is represent the gas in place. The formula is so easy because it's the area by for the thickness, for the effective porosity, for the anti-G, for the volume saturated by porosity, for the porosity for the all of grains saturated by gas. So the summary step, we have evaluation goal, the true sand porosity, the input data in this case is triaxial resistivity and density, with interpretation with Klein-Thomas-Stieber models, and segregated for laminate shale volume to isolate the clean and sand properties. The TOC is another important parameters. So it's clear that, as we just say, we underline that the migration stopped. So migration, in this case we have the migration from the sands to this layer, but effectively we have the potential to develop through sands. So finally what we decide to do, we decide to choose and to maintain these two parameters, the TOC and the total gas, in place. So the total gas in place is derived from sonic density and I-res gamma ray, and the total gas instead of this is calculated by the nuclear magnetic log free fluids, and we have finally the formula applied as we just said. First scale topics is define the geozone to achieve the IS performance. IS performance define the economical performance of single layer. Economical performance means financial recovery for a single layer, cost of operation, safety for a single layer, factory safety for a single layer, and quality of gas. As we just say, we have this situation. We have a sandstone up, sandstone down. Net pay, so in this case, the net pay for sandstone is 0.3. The thickness is around 20 meters. We have a high value, but the trouble that is a high value of zulf. So the high value of zulf drastically reduce the quality, and finally influential the net pay. The claystone, in this case, the thickness is around 33 meters. You have a low porosity, microgas bubble is another trouble. We can have also this, the microgas bubble. The claystone, so finally you can use this, and we can have also some thin quartz sandstone, single layer operation that we have no production in this case. So the matrix make a resume of cost and risk production matrix, low, moderate, high, very high, and finally I show you how you can apply to this case. So defining a geozone for integrated evaluation service, so IS is the meaning of that. Integrated evaluation service is the process of partitioning a subsurface interval based on a specific geological and petrophysical risk to optimize financial and operation outcomes in a complex turbidite sequences. So especially in this case, if the geozone is just in the depth interval, that is the risk to manage the environment, to compromise the wells, and like this. Summary of table. In this case, what is the pillar? You can have a financial operation when the NTG is maximum than 10% and also saturation, which will be the scientific tool that used to measure that, magnetic nuclear logs for free fluid, the triaxial resistivity. Operation, the deep and fastest continuity. You generally use azimuth or gamma ray resistivity. The quality, signal to noise, or also the presence of Zulf or like this. And safety, also the pore pressure and the fracture gradient. How to manage the risk zone and define the depth interval, while the drilling strategy and evaluation are governed by the interplay of rock strength, geomechanics, and fluid potential presence. In this slide we analyze the real case, so we are defined geozone of example of confined channel sand. As we just say, we are operated in progradation. So we have a channel sands. In this case, we have a channel sands at different depth. One of these channel sands is recorded between this interval of depth, navigated through the georesistivity image, and georesistivity image navigated into the channel, in the axis channel, while managing a narrow pressure window and resolving the thin bed plate. So we have two types of characterization: the petrophysical characterization, the rewards in geozone. So the turbidite sequences transition from distal level deposition to proximal channel axis. So it depends in which part of channel you are working on. So the features is massive to be laminated in sandstone. We have also the IS, the Integrated Evaluation Service. For this case, we apply the Integrated Evaluation Service for all of the channels. Real-time level D is intended to distinguish between low resistivity pay caused by conductive clay lamination, low resistivity pay, and true water bearing zone, which will be the risk that we underline this zone. We are overestimating, for example, we can have the contract case that is overestimating the water saturation due to the thin bed effects. And this is a clear data that you can resolve only for the cylindrical radial mapping of porosity. And mitigation use triaxial resistivity. So you can use also triaxial resistivity to calculate anisotropy and correct the saturation. For geomechanical analysis, we have other risk that we have managed in this case. The sand shale interface in this zone creates significantly stress concentration. So we have a stress concentration in sand zone. The stress profile you can be recorded through the sonic logs and like this. The shale are overpressured. The shale is in condition of overpressure, and there is also the water. So that's what this means. When you are effect drilling, you are not put in the same time the casing and you can have a collapse of wells. So while the sands are slightly depleted, for example, by the 13.8 part per minute due to reproductive fields. So it's clear that you need to define the stability window, that in this case we are called the safe mud weight window. So the integrated service evaluation with real-time LVD sonic wells with compractional analysis strength and shear waves is used to update the safe operation window dynamically in real time, using, as we just say in the next slides, the as using, as just saying in the next slides, the GI tools, the decision tree tools. What kind of risk we analyze? We analyze the bore breakout in the shale or loss circulation, fluids loss into the high permeability sands if mud weight is too high. Okay, I have also some animation, but I don't show you because it's covered by secret. Geozone analysis is essential for a step-by-step economically logs and reservoir calculation. And we can summarize all operations with the matrix risk analysis and cost. Finally, all of this we are seeing a value for a single operation. We define the geozone this, and we are seeing a value for a single operation of stabilization, of reduction of pressure, of like this. So the risk management assessment of the single zone in a confined channel sense. So we are working also in this part of in this part. We are still working in this part. You have this situation. So we have the lithophages and petrophysical rewards interpretation. Laminated pay. It seems that we have a good condition because the laminated have a good value of pay of TOC and pay, but there is the trouble of geomechanical stability and the geomechanical and boreal stability with the overpressure water and the risk of sliding of creating the shale overpressure. So we have defined, finally we define, we have this situation, we have a narrow pressure window, shale breakout zone, the same fluid zone, and finally we have the geozone definition. Make attention to this interval, the GZ, the defined GZ3. We have the optimized, here we have the optimized perforation. Here we have some petrophysical trouble, and we have a slow, make a slow perforation in this case because you have the overpressure. You need, while perforating, also apply the casing. I don't show you all steps because it's really crazy. So finally, the economical zone performance outcomes. Finally. So you have the quality of computational egg field, the operation zero packing, and finally NTG that in this case the NTG is measured than 50 meters. So the pay zone is measured than 50 meters. Effectively, you can consider this part, and because the migration tops from here, and you can isolate this. Geozone analysis is essential for step-by-step economical logs and reservoir evaluation, and we can summarize all operation with matrix risk analysis and cost. And finally, I show you how can summarize all of geoeconomical analysis with matrix risk and cost. And also to have some indicator of financial performance for single geozone. For example, when net pay of layers is measured than 50 meters determined by geomechanical models. Okay. Final indicator in ES impact indicator for we are going a very refined model, but we need in this case special casing. We are consider all of thin bed layer of minus than 1 meters They evaluated the rewards, so top row represented by the physical success, in this case resolving the equation of the geomechanical stability and the presence of a fluid by nuclear magnetic logs, conducted to the resolved also the gas emission in place. It's calculated as 1 billion facts, with an increase using these techniques. We have an increase of measured than 10% over standard conventional models, and the cost of risk mitigated with operation savings. So we are also mitigation all of risk. The middle row is the geomechanical saved cost by strictly heading the safety MFD window. You have some window that you are be casing during drilling, and after will be casing during drilling, and after fracked in some direction. So the breakout event was avoided. This prevented an estimated of around we saved this cost. So go to the financial indicators. Our financial indicators. So the financial indicator is much more important for the finally startup of project, for the complete start of project. So financially we verified the 50% of high gas volume. So we have an increase of plus of using this approach and this screening. You have measured than 10% of gas in place resolution. The operation maintained the constant DSD. About the geomechanical stability, we are near to the zero operation geomechanical stability, avoid packing off and wash out in G3 shale zone. We remember the G3 shale zone is the mixing zone, is this zone. We have a digitized channel into Seedstone Clayston. We are avoid all of geomechanical operation, navigating the narrow at 0. Parts per million without incident, and validate the real-time sonic. So the quality, we resolved the water saturation in laminated bay that we have minus than 50% than conventional models. And so this is the final structure that we are provided to this project. Our final indicators transform perform. We have a clear resume from the geological data, geomechanical and petrophysical data. We can be valorized by us and also by the interpreters by also this kind of approach. Thin bed sands with the oil and the calcareous cement. We have a microscale, the calcareous cement and calcite, while in this we have also some sampling that was analyzed by laboratory. This is a thin section. You have oil saturated calcareous cement occlusion in this part, oil saturated calcareous. You have the treated quartz because this is a ramp. This is transported by that. The interbedded shale lamine, that is this interbedded shale lamine. So the thin section allows to understand which is the real situation of this deposit. The integrated evaluation service resolution of true pale. So this is the next step. The first step is regarded by the gas. The second step is to evaluate the potential of shales in oil. It is another step that we are not finished, we are just conducted until to now. The clean sand, so we have a JIP of 11% resolution for interbed shale laming. The clean sand laminated thin bed oil sands, in this case with the Steuerberg plot, we are plotting the thin bed oil sand versus the calcareous. So the clean sand is located here, and we have also the laminated sands that we have with bulk density between 0.12 to 0.8. But the complex, but the situation is complex between geomechanical by pore pressure stability. In this case, we don't have complex for pore pressure stability. The geomechanical analysis of the trial axis resistivity show you there is some anisotropic layers, especially in northwest direction. But is normal. This analysis is not is still open. Gas, for gas is the analysis is closed, and we have the results that I show you. That is that I show you the financial statement is totally positive, and for the oil we are still evaluating, but we are probably not developed at this moment. So how finally the indicators transform the performances. So finally we are make measurements of all of layers in the performance using different scales of resolution. Make a step back. You are starting for drilling assessment. When you do drilling assessment, the style resolution is around 10 meters. Okay, you're starting for drilling assessment by seismic, magnetic, and gravimetric data with maximum 10 meters resolution XYZ. After we do the drilling assessment, we do the risk assessment, and so we evaluate the TOC zone of compression using an elastic inversion like this. After we do drilling exploration, and so we make a high resolution of this using also possibility of boundary wells. But the integrated performance, and we have a sabermetrical resolution with the cylindrical volts of acquisition. But finally, IS performance, integrated performance, means aligned financial operation, safety and quality at the scale centimeter, because in this case, in thin bed turbidite sequence, we are working at centimeter scale. So what we underline? We underline, for example, geomechanical vibration and the effect on change on calcite, the overpressure, the shale, the high variability of PGFG, the washout in shale. There is also another trouble. There is washout shale varied by image fidelity. DS triple stream integration, multimineral plus anisotropy give this final value of creation. And we have several tools that contribute to this, like spectral gamma ray for anisotropy model, LWD sonic image, a real-time geomechanical model, and ultrasonic image and caliper logs. We have an outcomes graph of metric impact, that is the real gas volume present in place, and the pay and an estimation of pay zone. We have also the successful of no of CNIS or loss by the different depth. Finally, we have this value. What tools we are using? We are using the tools that we are developing, that is the decision tree, support for geomechanical zone, the JETS evaluation, with price focus industry, oil and gas. This is tools that we are developing, and the input data, this is petrophysical data and geomechanical data, supported with internal ENG, with mapping the anisotropy and all of this. You can have a free type response. Yes, this geozone is commercial. Resolve reservoir by derivative the effective porosity and the content and the percentage saturated by water. We calculate GIP, extract the value, the correct value of total recovered gas. I want to remember you that the GIP, the gas in place, not all the gas in place, it will be recoverable. If yes, all parameters check positive, commercial pay, but conditional by risk. We can have geomechanical risk, stability analysis, stability risk, narrow mud weight window. As we just say in the previous case, when we are analyzing, for example, a zone with a fracture. In the fractured zone, you have a part that was re-empty, so you need to analyze this kind of sediments, the stability, and the compactation. Or also in this case, when you are in this particular zone, you need be to attention. So, if your parameters check now, we have sub-commercial pay, tight reservoir, high saturation of water. So the Thomas-Tibber relation and magnetic nuclear log indicate free fluids circulation and confirms high matrix risk. So we abandon, or we make an explorative, we abandon this or think another solution. Integrated support to geomechanical, as we say. Okay, so these tools that is called the decision tree, petrophysical and geomechanical tools, allow to define the geoeconomical zone. That is 1 for the very paid zone, 2 for the zone that make attention and stabilization or other works, and 3 for the zone that the cost operation exceed probably the engage of successful extraction. Finally, we are pleased to present what we are developing for Waterford, and the key topics is the IsoParker and mini Frac plug. The subtitle we have choose is give value to every thin layers. It's clear that after this experience, especially for the first part of gas evaluation. We need to do value for a very single layer. So the IsoParker is the best way to isolate a thin layer with the high TOC value and put into them mini frac plug. Why we need to isolate it? We need to isolate when, for example, the IsoParker isolated thin sand and siltstone layer with high TOC or high gas in place. The technology that we are developing is very simple. You can use that. It's clear when the wells is just refined, and we have the IsoParker thin layer TOC. We have the high TOC sensor layer. We make like a plug, isolated the layer that you are interested. We apply a grip mechanism supporting also coring in this phase. And why we do this? We do this for this region that I try to explain. First, when you have all of this laminated, but you have also the sand, thin sand with overpressured fluid. In this case, we need to isolate it. If we want to start production, for example, of this interval, you need to isolate it then, isolate it from upper part and middle part. Consider this like the same. Repass with nuclear magnetic logs. Repass with nuclear magnetic logs or caliper logs. So have a cylindric plot of correct porosity and jets evaluation, and after that you can need to isolate the part with IsoParker. You can isolate the part with IsoParker, and finally you can apply in internal part of IsoParker. You can bumping the frac plug. Frac plug is a system that is allowed to auto-dissolve. With you can arm this with microcarica and in all conditions and all wells diameters. So you can use. We are developing this because Waterford is one of the leaders of the well service around the world. We can use IsoParker also, and we are testing IsoParker and frac plug dissolve also in ancient wells. Frac plug dissolve are allowed to be operated in all conditions and all wells diameters. So also in all the wells, you need to consider that the diameters in the parts, the diameters of wells must be changed. A great difference between now. So the advantages of the system that you can be applying all kind of wells. The plug is dissolved, is ideated to be dissolved and applied just, and now is just to test it in 100 wells for stimulation project. So the frac plug is that and can be clear working. Can be frac in a predefined direction. Allow is testing in old wells to stimulate the production from, for example, siltstone rock. The times of application, the medium times to goes in wells, frac and dissolve is around 2 or 3 years. It depends on depth. We have a schematic situation. We have the well bore casing, the frac plug dissolve system, the tubbing, the system for the active dissolution, and we can frac from diameters to 30 centimeters to standard diameters that now the standard diameters are 320 centimeters. So the time of dissolution is around 4 hours. 4 hours when just counted from just when we are operated. Frac plug is our ideas, and we are patented for waterfall. So the slogan is clear, give values for every fin layers. So IsoParker and mini frac plug allow waters and companies to maximize the value of fin beds and reservoir. If you have, for example, a zone with a good net pay of 0.5 but need to be consolidated today or fracked, there is another important consideration that the company do. When we do economical and integrated service analysis, we evaluated all conditions and all economical aspects of production layer, and future production layer analyze also what should be the evolution from the actual reservoir to the migration zone to trap and other areas. What we want to underline that probably mapping, for example, in this way, reservoir with the steering or have these kinds of map in this way, allow all of companies and all of companies served by Waterford or Schlumberger to be sure that, for example, in this moment the price of gas of oil is around $120 is too high. It's true that's too high, but in the past it was an half. So we probably have a zone with good net pay. You are sure that in this sense you can have a cheap gas in place, an important gas in place, instead the anisotropy of layer and particular overpressure condition like this. So don't despair. Isolated now and fracked tomorrow. So this is the slogan: isolated now and fracked tomorrow, when gas price is too low, or the matrix of operation analysis permitted this. So with the IsoParker system, we can support scaling and maximize the value of every fin bed reservoir. Thanks for attention, and if you have a question, you can write me or chat.